Hello and welcome to E233. I'm your instructor, Gregory Myers. This video, we're going to take another look at an older version of our P5 project, the one that focuses on our physics demo. And specifically what we're going to do in this video is we're going to focus on our projectile _2D_ version 4. This video is part of a larger series of videos that focuses on the fundamentals demos. And particularly in this video, we are now looking at how to utilize parallel arrays to be able to accomplish multiple calculations and then ultimately use the values from those calculations in our calling function. And so you'll take a look at the function signature for our projectile 2D version 4. It's actually quite long. It has quite a few arguments, a combination of which are going to be by val, particularly our v init and theta, as well as our n, which keeps track of the number of elements in each one of our arrays. And then we're also passing a time, a y time, vy time, as well as an x time and a vx time vector or array. The idea is that these 5 parallel arrays are basically kept in sync by our n. Now, one thing to note here is n is the number of actively used elements in the array, not the total number of elements in the array. So actually what we're going to do is we're going to define these arrays larger than what they actually need to be. But for right now, what we want to do is we want to focus on how this function will actually utilize them. And so you'll see that I went ahead and improved my comment block in front of the function, providing not only the name of the function, short description, and then went through each one of my arguments. I encourage you to go ahead and take a second to do the same. And what we want to do once you get done with that is we want to jump into triaging or validating each one of our arguments. Now, I encourage you to go back to the slides that I provided on the physics demo. But fundamentally, some of the things that we want to check are that our v initial is in fact positive. We just don't want to handle the scenario where it's negative. And we also want to make sure that our theta falls somewhere between 0 and pi. Once again, we can handle it a number of different ways, but just to keep this problem simple, those are going to be our constraints. Additionally, just like in the earlier one, we want to assure that we at least have 2 values in each one of our parallel arrays, just because of how we choose to present the data when we get finished. And so the n must be greater than or equal to 2. So let's go ahead and get started by going through these arguments and essentially validating them. And so to begin with, what we'll do them in order. We'll check that our v init is in fact not less than, and I guess technically for that matter, we probably should consider the scenario of also equal to. So in other words, that our v init is not less than or equal to 0. Is we simply use printf error. Please provide a positive initial velocity. And then, more importantly, we simply say results are then equal to exit failure. Continuing along with that, we'll check to see that our theta falls between 2 values. In other words, we want to make sure that our theta is in fact not less than or equal to 0, or that theta is not greater than or equal to, and in this case, what we'll do is we'll actually use a constant that is available in the math.h. I'll go ahead and take a look at it just to remind everyone. But you'll see here that our m_pi represents pi in radians. And so basically what we want to do is make sure that it is not greater than pi or 180 degrees. Coming back here, then we'll just simply say then printf error, please provide a value for theta from 0 to pi. And then once again, results equal to exit failure. Now for the arrays, to validate them, I'm going to keep this one fairly simple. I'm going to just check to see if they are null, and I'm going to do these all at once. So this one's going to get a little long here. So in other words, if time is null, or our y time is null, or our vy time is null, x time null, or vx time null. Any of those scenarios, which are very unlikely to happen, but we just simply want to check. If any of those scenarios are true, we simply have a printf that says something similar to what we did earlier. If you want a little bit of a reminder here, it basically says, please provide valid arrays. At this point, basically, you've got something wrong with your memory management. So please provide and more importantly, we want to say results are equal to exit failure. I seem to have a typo here. Let's see if we can't find this before we go any further. I think I've included an extra. Let's see if we can figure out. So this matches, there's our print statement. All right. 1 second here. This is just going to be a matter of figuring out where we have mismatched our parentheses. We're going to go ahead and throw the else in here just to see if that helps. And there we go. We're missing our semicolon there. You were probably about ready to reach through the screen to help me out there. Let's see if we've got any more problems. Let's go ahead and build this just to see if that clears any of them up, or in fact does not. And so at this point, then semicolon is missing. There we go. Once again, else if. Okay, so there we go. Sorry about that. Sometimes we just have typos that we have to get through. All right, and at this point, then the only thing left to check is going to be our n. And you can actually go ahead and combine the two cases. In the earlier example, I did not. What we can do here is we can actually look at the scenario where n is less than 2 or n greater than n max. And to do it a little differently than we did before, we can have a printf that says, error, please provide a valid n from 2 to %d. And our %d is simply going to be populated by whatever that constant is for n max. Now, under the else, if we've managed to make it this far, we want to do something. Well, and what does do something look like in this particular scenario? Well, what we want to do is we want to first go ahead and calculate our t final from our Vx init and theta. We're going to break our Vx init and theta up into Vx init and Vy init. So the idea is that we have components of our velocity vector in the horizontal and the vertical directions. That's part of the reason why we wanted to stick with theta from 0 to pi and a positive value for our V init. And then from there, then once we have our t final, we break it up into segments of length t delta and simply do like we did with the first version. We loop through starting with 0, using an index variable up to the number of segments that we want, and essentially calculate then the time, the y time, Vy time, as well as the x time and Vx time. So we'll need a few extra variables here. So let's go ahead and add them. We've already have our results variable. We might as well go ahead and include a t init, a y init, Go ahead and include an X in it. Some of these are going to be unnecessary, but just allow for some future expansion. Then we also have a VX init and a VY init, which we will use. Start off with our VY init and VX init. But then we also need a T final as well as a T delta. And then lastly, but not least, we also need an index to allow for us then to loop through the elements in our parallel arrays. At this point, let's go ahead and calculate our VX init, which is going to be simply our V init times our cosine of theta. Likewise, our VY init is going to be equal to our V init times the sine of theta. And we use the VY init ultimately to calculate our T final, and that is simply handled by then -2 times our VY init divided by our constant for acceleration in the Y direction. And from there, then we can calculate our T delta. Our T delta will once again just simply be our T final minus our T initial divided by N minus 1, where N is the number of data points and N minus 1 is the number of segments. Now, at this point, we have not initialize some of our variables, and so we have to be careful, particularly our T init. And so we've got a couple of options. We can simply go through and initialize all of our declared variables, which is probably not a bad idea. It's the safe approach. And so what we'll do here is we'll just do each one of them, regardless if we anticipate calculating with them or not. And then we can do the same thing now with our Y init, our Y final, or actually our X init, our VY init, and our VX init. Once again, in some cases, we are doing the calculations or the assignments, so this is kind of a bit redundant. And a good example of that is also by initializing our index, which we will ultimately use in a loop. Once again, it's just a safer approach to go through and initialize all of your variables after declaring them. Now, at this point, you've got your T final and your T delta. We can go ahead and add to the T final then our T init. In this case, our T init is in fact 0. But what we can do now is we can start our for loop, and our for loop is going to start off at 0. It's going to continue up to, but not including n, and it's going to increment by 1. And then inside the for loop, we simply one at a time update our parallel arrays, starting with the time. So our time square brackets index is going to be equal to our T init plus whatever the index value is times that T delta. And what we can do now is we can use the current value of time over and over again in each of our subsequent equations, starting, for instance, with our Y time. Our Y time is just going to be our Y init plus our VY init times whatever the time is, plus the 1/2 AT squared, or 0.5 times our AY times the power function of the time raised to the second power, or squared. Now, continuing with this, then we can do our VY time. Our VY time is just going to be our VY init plus the AY times our time value, our current time value. And the good news is the equations for the x direction are very similar. We have our x time, and I apologize here, I've made a mistake here. It's x time, and I've forgotten my indexes here, so it's y time and vy time, both of which require the square brackets index. So my apologies there. And we do the same thing now for x time, square brackets index is equal to whatever the initial value is for the x, which in this case is going to be 0, plus then our vx init times whatever the time is, the current time, plus then 0.5 times ax, which happens to be 0 for this particular example, times the power function of the time raised to second power. And we do the same thing now for our vx time square brackets index, which is just going to be equal to the vx init plus our ax times whatever the current value is for the time. And basically you'll notice here that our velocity in the x direction is constant because our ax is equal to 0. At this point, then basically we're done with our calculations. It's probably a good idea to go ahead and build this just to make sure that we haven't made any mistakes. And we have green, that's always a good sign. So now let's go up to our main and let's then call our function given either the /i or the /p options. Now, before we leave here, I want to take just a second to point out that you'll notice that we once again have no printing inside of the function other than the error messages. And so the idea here is that all of the responsibility for the tables and for the file IO fall outside of this function. So let's go up to the main, and then let's go ahead and add some variables, much like we did earlier. We can already guess what those might be when it comes to the two-dimensional motion. We already have our y time and our vy time, so we don't have to add those, but we do need to come along and we need to add our x time. Once again, we're going to make it far larger than it needs to be. And we have our vx time with our n max. And then we'll see if we need any more additional values, but most of them, or variables, most of them are already provided. And by the way, I want to go ahead and clarify one thing. It isn't necessarily that these are too large. It's just that if the user only wants to have, let's say, 11 data points, then we've allocated enough room for 100, then effectively we are being inefficient with our memory. And so we can't necessarily know what the user wants to put in at runtime and until runtime rather. All right, so let's go ahead and go down to our 2D options /i. We were set up and ready to call our function. So let's go ahead and say results are equal to projectile 2D version 4. We want to pass to it whatever the vinit was that was collected from the user, as well as the theta that was collected from the user, the time vector that we created earlier, and the y time vector. Yes, we're borrowing those from the 1D. That's perfectly fine. And then the y time. Now we have our x time vector and our vx time vector. And then lastly, then we need our n, which sort of plays as a traffic cop, if you would, to keep track of the active number of elements in our parallel arrays. Now, as before, there's no reason to print out a table if our function failed for whatever reason. And so we simply check to see if our results are equal to exit success. And if they're equal to exit success, do something. Else, we have a problem. And for we have a problem in this particular scenario simply means that we have a print statement that says error, failed to run the function successfully. And once again, we have some print statements already inside of our function. So hopefully combined with that, it'll give the user some idea of what did in fact go wrong. Now, under the do something part, we want to leverage our P5 sample and look at our table once again. As a matter of fact, if you had done perhaps the right thing earlier, you probably made a copy or backup copy of your table. This would probably be a great time for us to go ahead and use it. And the idea then is that we simply want to populate this table with the values starting with our T init. And so what we can do now is we can say printf and our T init, which is in seconds. And we'll once again use the same format spec of the percent 8.4f followed by the new line. And for our T init, we can simply go ahead and use our time vector square brackets 0, which is essentially the first element in our time vector. We can do the same thing now with our T final. And once again, we are using the n-1 element, where n is the total number of elements in the vector. At this point, then, you can go ahead and go through each one of your vectors. We could probably do a little bit of careful copying and pasting here. And so we can start off with our y init, which is in feet. This will be our y time. This will also be our y time. This will be our y final in feet. And once again, a little bit of careful copying and pasting here. We can repeat this for the x direction. And with the x vector, we can follow this up with our vy init and vy final. And both of those are going to be in feet per second. And once again, a little bit of careful copying and pasting and some selective changes. Then we can also do this for our vx init and vx final. And the only thing really left to do is to provide some of the input arguments, perhaps a printf with the number of elements, which is just simply n. The vinit, which was in feet per second, which once again we can do in the percent 8.4f, followed by a new line. That'll be our vinit. And then one last copy and paste, and it'll be our theta. And that will be in radians. At this point, we're probably ready to check to see if our 2D/I works correctly. So let's go ahead and build it. If we don't have any mistakes in here, at least it compiles. Let's come out to our console. We'll do /2D/I. We want the initial velocity, the angle, 0.7854, and the number of points, how about 11? And once again, a little bit of tweaking with the column, maybe push the number over a little further. But we have our vinit of 100, the theta 0.7854, tnet 0, t final is 4.39 seconds, y init 0, y final should be approximately 0. We notice that our vy init and vy final are roughly the same. That's one of the reasons I picked the 0.7854 as a good demonstration. We kind of guess what those values should be. And our x init 0, x final is 310, and so on. Seems like we have this part working correctly. And so once again, a little bit of careful copying and pasting. And we can push this down to the /p option as well. But before we go any further, let's go ahead and handle that file IO. And if you recall from the previous video, we went back to the P5 instructions. And we looked to see the number of columns expected. In this case, for the 2D version, it's going to be 6 columns with n rows, where n is the number of data points we're trying to calculate. And we want to have the index, the time associated with that index, the x and y values, as well as the vx and vy values. So once again, what we're going to do is we're going to go ahead and open the file for writing using fopen. We want to carefully use the file name that I've provided in the instructions, whatever that might happen to be. And then we want to open it for writing. Very first step, once we check to see, the very first step that we want to do is we want to check to see if the file was successfully opened. And to do that, we check to see if our output file pointer is not equal to null. And if it is not equal to null, we want to do something else. We have a problem. And once again, what does that look like? Well, that simply is a print statement in this case. It says error, failed to open the output file. Followed by a new line. Now, under the do something part, the first thing that we want to do is essentially remember to close the file before we forget. And then we'll build a for loop using the index variable to loop through each of the elements in the parallel arrays, starting with index equals to 0. Index less than n, where n is the number of elements in the parallel arrays, and then index plus plus. And then using fprintf, we have the output file pointer, and then very carefully the format spec again, with %d being for the integer, the %8.4f being for the doubles, separate each by a comma for a total of 5 values, followed up by a new line. We're going to go ahead and put the values on the next line just so that this doesn't end up being too long here. But the first one is the index. The second one is the time at a given index. The third one was going to be x time. So again, you can go back to the instructions just to verify, but there'll be x time at a given index, y time at a given index, vx time at a given index, and then lastly, vy time at that same index. At this point, let's go ahead and build it once more. Once again, no bugs. Let's go ahead and rerun this. Initial velocity of 100, angle 0.7854, number of points 11. And if you go back to your folder, you'll see there's now a Projectile 2D version 4.csv, and there's 1, 2, 3, 4, 5 columns, and we've apparently missed one here. So it's going to be the 1, 2, 3, 4, 5. Which one did we miss? So we have our time, our x, y. Let's go back here one more time. X time, y time, vx time, and vy time. So 1, 2, 3, 4, and 5. All right, let's see what we've missed here. So 1, 2, 3, 4, 5. I was not careful enough with my copying and pasting, and I accidentally left off our 6th column. All right, so simple problem to solve there. Let's go ahead and build it one more time. Let's run it. 7854. And there we go. 1, 2, 3, 4, 5, 6. So now we have our 6 columns. At this point, the only thing left to do is a little bit of careful copying and pasting. And once again, this approach does result in a non-trivial amount of duplicate code. We're not going to get around that problem here. We just want to carefully bring this down to the parametric block, copy and paste it. Once we know that it's working correctly, build it. And then we can come out to the command line, and instead of doing the /i switch, do /p, where we provide the initial velocity as well as the angle and then the number of data points. And I'm going to go ahead and provide a different number here, in other words, 21 again, and you'll see that our CSV file has in fact been updated. So hopefully you found this video useful. As always, if you have any questions, comments, or concerns, don't hesitate to contact me, and thank you for watching.